Hello world, this is Craig. So the punch card and the paper tape predated the electronic computer by a couple of centuries, and so I don't think it took any great vision when the computer came out to start using punch cards and paper tapes for their data storage. You would use punch cards if you needed more random access, like customer records for a database sort of thing, and you would use paper tape if you were doing programming or other things that were serially accessed. But at any rate, by the time the microprocessor came out and the industries that were using it, many of them already had paper tape machines. They would have punches or they would have a teletype or something. And the paper tape was very nice. I think if you were going to send something to somebody, the paper tape was the preferred format for it. It certainly wasn't the perfect medium. You'd have rolls of paper tape laying on the floor. It would wear out unless it was the nicer Mylar stuff. It would tear, and this happens to be oiled tape for my teletype, and so it's got an oily smell to it and an oily feel to it, and just not ideal. But nonetheless, if you were an industry or a high-end user, you probably had a paper tape reader. Heathkit even had a paper tape punch reader, and maybe you had a teletype. But as the microprocessors became cheaper, people were looking for another medium to use for data storage. I mean, after all, you had all these programs and all these games and all the stuff that you needed to store, and there wasn't a good way to do it. At that time, magnetic media was very popular. This is a 9-track tape, and so you can see the width of that. It's wide enough that you can store a byte and a parity bit on this just across it, and so that's a nice system for storing data. Unfortunately, 9-track tapes were way beyond the affordability for small users, and so the need came out for the industry and consumer grade method of storing data. And of course, that's where the cassette tape came in. So if we look at the compact cassette tapes, this is just a regular one. You can see how wide it is, whatever, 3/16 of an inch. Look at that compared to a 9-track. So obviously on the compact cassette, there's not going to be enough width of the tape to be able to store this in parallel format. So it's going to have to be a serial format when it's stored on this tape. The other problems you have is that the tape player is designed for audio frequency response. It's designed to get rid of noise, and it's got filtering, and so everything in the electronics in this is essentially AC coupled and filtered for audio range, up to maybe 20 kilohertz. So you can't store just data on this in serial. If you just had a serial port and you tried to just store stuff on this as ones and zeros, it wouldn't work. This is only 2 tracks of data. There's 1 track when you have the tape in this way, and 1 track when you have the tape flipped over in the other way. Newer cassette players came out and they were 4 tracks, so you had stereo on each side, so you had 4 on this side, or 2 on this side and 2 on the other side, of course. But nonetheless, with the speed that this is going, a couple of inches a second, and the width of that tape, it's just not possible to store the data in parallel format, and even storing it serially has got some major problems. So let's look at a serial data stream and see what problem crops up. So this is a serial data stream, and let's say that this could be something like RS-232. Say that the line is normally low. We'll have a start bit, and then we'll have some data, and this is our data all the way through here, and we have a stop bit. And the way we convert this back to data is we have to come through, we see the start bit, and we count a timer. So we time for a little bit, and we take a sample of the data, and it's either low or high. We time for a little bit, take a sample of the data. In this case, it's high. Time for a bit, low, time for a bit, low, high, high, low, high, and then we are done with that byte, and so we would have our stop bit down here. So this is great if you have very good control over the speed of this tape playing back, and if you had a 2-track tape from the very beginning, you could have had 1 track that was the data and another track that was the synchronous data of when you would sample this, and so you would have a little spike of data or something every time that it was time to sample it. So then if you had wow and flutter, and this temporally kind of changed it, accordion in, came out as the tape sped up or slowed down. If you had these little timing spikes that you knew when to take the measurement, that you knew when to sample the data, it would work out okay. But a lot of these tape players, back in these days weren't stereo. They didn't have this second channel. They only had one channel to work with. And of course, we know this is mono because we can look at the microphone. This is the microphone for it, and this is the interface for the microphone, and it's just a mono plug. This one over here is for the switch to power it off and on. So, this was a mono tape player, and so we only had one track to play with. So the fundamental problem is that when we're playing a tape, and if there happens to be, sometimes you would see on a take-up spool it would get a little bump on it, and so the tape would jump across that, or the tape gets a little bit worn, or your batteries run down, or the tape is going faster or slower, its speed control isn't all that great. The problem is it becomes impossible to time this. It's just as if your baud rate were off. All of a sudden you would start getting junk on your tape. And storing things on tape was frustrating enough, especially like this tape player doesn't have a little readout of where it is on the tape, so it was really, really hard to find programs if you had to speed forward and listen for when the next program started. So it's frustrating enough in the best of conditions, and then when you had a cheap tape or a worn out tape or a cheap tape player, it really started to become a problem. So there were a number of formats, and we've heard of the Tarbell format and the Kansas City, and those were probably, I think the Tarbell was probably the best, and Kansas City was right up there. There's another format, and I don't know exactly when these all came out compared to each other, but Intel also had a format that they created, and its claim to fame, it wasn't exactly quick, but the hardware was very simple for it, and it was fairly robust. So let's look at the Intel format and see how they stored and recovered tape data. So this is a board for the SBC-85. It's based on the Intel format. This is just essentially right out of their data sheets from the MCS-80 series or MCS-85 series microprocessors. So this is all just Intel reproduced, basically. But what they decided to do was push all of the complexity onto the microprocessor and make the hardware as simple as possible. So this utilizes just a quad op amp, has one op amp for the output, and then 3 for the input. So let's look at how Intel decided to store this data. This is our data coming along, and we're going to have a logic 1 followed by a logic 0. Say we've got 2 logic 0s and then a logic 1. What Intel decided to do was, let's take each of these bits and essentially bracket that bit with a start bit and a stop bit. So we're going to divide that into thirds. Each is going to have a start, it's going to have a stop, and then it's going to have the data bit in between. So essentially what this one bit would then look like is it would come along, we would have a start bit, look like that. We're then going to have the data bit, in this case it's going to be a logic 1, and then we're going to have a stop bit. So the stop bit is going to go back down to here. So that's the first data bit right there divided into thirds. This data bit's a 0, so it's going to have a start bit, and then the data bit is actually a 0, and the stop bit is a 0, and so the second bit would look like this. This bit would look the same. It'll have a start bit, and then it'll have the data bit and the stop bit. This next one is going to have the start bit, it's going to have the data portion, the stop bit, okay, and it'll go on like that. So what we've done is we've taken each bit, divided it into thirds, and that third is always, first is the start bit, the last one is a stop bit, and the data bit is in between. Now of course we can't write DC to the tape. So rather than just have it go as a logic 0 and a logic 1, since we can only put AC on the tape, we have to create this as AC, and we call that a burst. So what we're going to do is, when this is logic 1, we're going to oscillate that. And so the microprocessor is bit banging this out. It's going to put out a square wave that's in the range that the tape can pick up. In the examples that we did for the software, it's a 2 kilohertz burst. So when we want this to be a logic 1, we're going to put out a 2 kilohertz burst square wave. We want it to be a logic 0. It's going to be nothing, a pause. So then this would be another 2 kilohertz square wave, and then a pause, square wave, pause, and that's all square wave. So we can hear this on the tape. If we listen to this, What we have on this tape is a leader, and the leader is just a straight 2 kilohertz continuous frequency, and I mean it's really annoying to listen to. And then it's going to go into the data portion, which sounds more staticky. So if you remember, listening to a penny whistler, at first you have the high-pitched kind of carrier or the solid frequency, and then it would go into the data where it's more staticky. So let's listen to that on the tape. First we're going to have the solid portion. It's going to be a high pitch, and then it'll go to the staticky, which is the data portion. This is the leader portion. And there it just went into the data portion. So you can hear the obvious difference between the solid frequency and the data frequency. So in the second part, what we're hearing it is put this out a combination of bursts and pauses. We have a lot of the software on the SBC-85 website. We have routines for writing the leader. The leader puts out the 2 kilohertz burst, and then it counts down in ASCII from 9 to 0, and then it ends the leader and begins the data portion. Then we have routines for writing data out to the tape. And so you can tell already we're bit banging this, and writing to the tape is extremely easy. We just pick a counter, and we just pick a frequency that we're going to output. And if that is a logic 1, we output for 2/3 of some time period the logic 1 or the burst, and then we wait for 1/3 for the stop bit. If that bit that we're sending out to the tape is a logic 0, we do our burst for just 1/3 of the time and then pause for 2/3 of the time. So it's really easy to send the data out. Now reading the data back in is fairly simple too. What we do is we wait until we see a rising edge, which is going to be the beginning of our burst. And as soon as we see that rising edge or our bursts start, we start a timer. We start the timer at 0, and we start counting down all the time that we see this burst coming in. So here we would start counting down, and let's say that when we get to a third of the way through, we've counted down to minus 3,000. Another third, we're now down to minus 6,000. That goes away and we get a pause, so the burst has gone away. We start counting up. So when we get to this point right here, which is easily recognized because we go from the stop bit to the beginning of the next burst, so when we see that transition, we know that we finished this bit. We look at our count. In this case, we were at minus 3, minus 6, counted back up. So we were at minus 3,000 for that bit. We see this transition because the only time we're going to see this positive transition is when we are starting a bit. So we see this transition again. We start counting. We zero our counter. We start counting down. Here we're at minus 3,000. That goes away. We have silence, so we start counting up. Here we're back to 0, and here we're up to positive 3,000. We then see a high transition, so we know that's the start of another bit. We do the exact same thing, and we're going to get the exact same answer. We're going to get plus 3,000 on this. Another transition, zero our counter, decrement for that period of time, get down to minus 6,000, and then increment for that period of time. So now our final answer is minus 3,000. So you can see that in an ideal situation, all of our bits are either going to be minus 3,000 or plus 3,000. And that's going to tell us whether it is a logic 1 or logic 0. But we figured that this is going to be somewhat less than ideal, so we're just going to make the division at 50-50. If we're at 0 or below, this is going to be a minus number. And so if we just look at the most significant bit of that, it's going to be a 1 because it's minus. So this means that our incoming bit was logic 1. This guy, that bit, his most significant bit in the counter is positive, so he's going to be a 0. So this was logic 0. This was logic 0. That was logic 1. So when we're decoding this, it's very simple because all we have to do is have this counter. When we look for this rising edge, we know it's the start of this little 3-segment bit. We look at those 3 segments, and whoever wins the count, either counting down or counting up, the sign of that count or the most significant bit tells us the value of that data bit. And so this is very immune to wow and flutter. You know, we can squeeze this and stretch this quite a bit, and we'll get the same result because we're going to count for as long as this is high, and we presume that even if this stretches out a bit, this is going to be high for 2/3 of the time and then low for 1/3 of the time. And then the next bit, it can stretch out some more, or it can really shrink, and we're going to be high 1/3 of the time and low 2/3 of the time. So we've changed this from having to have speed control over the entire byte to only have to have speed control for this one little bit, which is really easy to achieve even on a cheapo cassette player. This is the board. Of course, we have a line going to the tape, a line from the tape. We can use the SID and SOD on the back plane to communicate with these jumpers, but since the SID and SOD is busy with the serial port, generally we would be using this interface that goes to the one of the interface ports, like on the 8155 on the CPU card. We have this quad op amp and then just the resistors and around. So it's a very simple card. But let's look at that schematic and see what we've actually got on this card. Here's our port coming in. We have our main data line. We have a jumper to either connect it to the SID and SOD or to that port. When it comes into our port, we can see it goes into this op amp, which is just a driver, and we're going to drive that signal capacitively coupled out to the tape, and by the time we come out, it's a 1 volt signal. So this is what a leader looks like, where it's just a 2 kilohertz straight signal, and this is what data looks like going out to the tape. And we can see that we've got a burst. This is a logic 1 because it's 2/3 burst. This is a logic 0 because it's only 1/3 burst. That's a logic 0 again. So this is what it looks like going into the tape when it is the data. And that's the second part of the tape we heard, where it was more staticky than just that one annoying pure frequency. So this output is simply taking the 5 volt burst and converting that to a plus and minus 1 volt signal to get recorded onto the tape. Now when we come into the tape, this is AC coupled. We come into this first amplifier, which has a gain, and it buffers it up to this line, but we can see that this also goes to this signal diode. So when it comes in and this is on the positive rail, this is forward biased, and so it charges up this capacitor faster than this little resistor right here is discharging that capacitor. Then when that AC swings low, this inverting amplifier is now at the rail, and so it's forward biased on its diode and charging that capacitor up. So we can see that when we're receiving a burst in here, either the positive portion of that waveform or the negative portion of that waveform is simply charging this capacitor up. As soon as we get to the pause, nothing is coming in here, so nothing is charging up this capacitor, and it drains down to ground. So this is how we get at test point 3, we'll see either these bursts and pause. So this is our data coming in from the tape. So we can see bursts and pauses coming in from the tape. And then this is at test point 3, where the bursts have been integrated into a logic 1 and the pauses show up as a logic 0. So here we can easily see that this is a logic 1 because it's 2/3 high. This is a logic 0. That's a logic 0, another logic 1, 0, 0, 0, 0, 0, logic 1. So it's easy to see just by looking at these whether they're logic 1s or 0s, because we only have to be able to differentiate between 2/3 high and 2/3 low. So it's even easy to do this by eye, let alone with the microprocessor. Then after that integration, we go through this last buffer that is swinging rail to rail, so everything here is going to be either at 0 volts or 5 volts. Oh, by the way, that's the nice thing about this LM324 is this is running off a 0 and 5 volt rail, so this doesn't require a bipolar power supply. So when it comes out of this last op amp, test point 2, we can see that we've got a pretty good waveform here that's running just above 0 and just below 5 volts. There are also on this circuit board some diagnostic LEDs, or just some LEDs that you can use when you're programming for various things. They're labeled as volume up or down and the status and the volume OK, but you could use those for whatever you wanted. Okay, so that's the circuit. It's very simple. You can see the board. This is the 100 millimeter square board, so they're fairly low cost. These are the $3 boards. Very easy to populate, no exotic components, and very easy to get going. We've got the software written for writing the leader. The leader just has that constant 2 kilohertz burst, and then it counts down from 9 to 0 in ASCII, and then it starts pushing out data. So we have the routines for the leader, we have routines to read the data and write the data, and then an example routine, and that's all in the utility file on the SBC-85.com website. All right, so that's the cassette interface, and that's done. These files are available for download if you want to make your own boards, or you can get these on eBay, or you can just ask me for these and send me an email and PayPal me for those cards. So these are somewhat available for these cassette cards. Now there's something else I wanted to show you. This is my next project, and this is an exciting project for me anyway. It's basically a pickup from a project that I was working on my first or second year of college, and this is a 1 megabit bubble memory card. The same professor that got me really into digital electronics, we sat and talked about this fantastical bubble memory that was going to be coming out by Intel, and we started some design work on a bubble memory card, but we never actually got the bubble memory modules. So many years later, I have a bunch of bubble memory modules. So here's one, for example. This is a 1 megabit bubble memory module, and I have the seed generator for this in case it's lost its seed, and I have the support chips for it. So at any rate, this is my next project. I've got the boards in, and you can see I've just started populating the sockets on it. But this is another throwback for me to actually finish this bubble memory module that I started decades ago, when the same time that I originally envisioned this SBC-85 concept and wire wrapped the one years ago. This was going to be a part of that plan, but it just had to sit on the back burner for a number of years. Okay, so this is my next project, and I'm really looking forward to this, and I will put this on Hackaday and also have a few updates on the SBC-85 website. Okay, so that's something to look forward to if you ever thought you wanted bubble memory, or even if you didn't. This is something that just not every grandmother has a 1 megabit magnetic bubble memory card. All right, well, that's all I wanted to share with you today. If you have any questions, let me know. And I appreciate your feedback, and let me know what you're thinking. Thanks for watching. Bye-bye.